Now to turn our theory into a practical circuit. Here is our original OR gate from the last session. All we need to do now is to include the NOT circuit by first removing the resistor R3 and the LED. We can see that R3 is connected to the positive rail and the collector of both TR1 and TR2. The LED is connected from the collector of both transistors as well, but remember that this device is polarity dependent, so we need to reverse its connection. The other end of the LED is connected to the negative rail, so we will fit a link between the negative connection of the LED to the negative rail. We can see this in our practical design. So connecting the battery will cause the current to flow to SW1, which is open. It flows through R2 to SW2, which is also open. Then through R3 and to the collector of both transistors. Since both transistors are off, a complete circuit can be made through the LED, which illuminates. So if the input is 0 and 0, the output is 1. This time SW1 is closed and the battery connected. Current can now flow to TR1, switching it on. Current continues to flow to SW2, which is still off. It continues to R3 and to the collector of TR1, but now TR1 has become conductive, which means it will cause a voltage drop across the LED, which fails to light. This means that when the input is 1 and 0, the output is 0. Resetting the circuit and closing SW2. Current flows through R1, but SW1 is off. It continues through R2 and turns on TR2. The current flows through R3 and to the collector of TR2. Once again, because TR2 is now conductive, it causes a voltage drop across the LED, which fails to light. Once again, if the input is 0 and 1, the output is 0. Finally, when both switches are closed, current flows through R1, switching TR1 on. It continues through R2 to SW2, turning TR2 on. It continues to R3 and to the collector of TR1 and TR2, causing a voltage drop across the LED, which causes the LED to remain off. So if the input is 1 and 1, the output is 0.